Alright, this is going to be the lecture video for Chapter 4, Two-Dimensional Kinematics. So we previously talked about motion in one direction, and we were only concerned with whether the object was going horizontal, was it vertical. Now we have to take into account if the object is now going at an angle or it's being launched. So now we have to take into account the x and the y components. So building off of what we did in vectors, now we are going to apply it to motion. So we're going to talk about motion in both dimensions. We're going to talk about projectile motion and its basic equations. What happens at a zero launch angle, at a general launch angle, and then just some characteristics about projectile motion itself. So if your velocity of your object remains constant, then your motion is along in a straight line. Right? So if we look at the turtle, right, he's going in a straight line, he's going at an angle. We can figure out his x and his y components using trig. We can do that for both position, like in figure A, we can find the x and the y. And then in picture B, we can find the horizontal and vertical velocities. So now when you see variables, you may now see y's involved. All y tells you is that this is the vertical component. It's still velocity, it's still position, it's just making it clear that now this is vertical. So again, like we did in vectors, motion that happens in the x and y directions should be solved separately. So if you're going to solve something in the x direction, you better just do it for that component. And if you have multiple things in the x direction, then you can put them together because they share the component. But you cannot find x and y per se at the same time for your motion. So for projectile motion, there are some basic equations or basic assumptions that we need to know. So just like I've said in previous lecture videos, we are going to ignore air resistance. This is going to be like we are in the perfect world. Everything works like it is supposed to. We are going to assume that the acceleration of gravity is 9.81 meters per second squared going down. And we're going to ignore Earth's rotation. That would just involve more math, and we don't need to do all that. So, if your y-axis is pointing upwards, then we can assume that the acceleration in the x direction is 0, and the acceleration in the y direction is negative g. So, for this perfect world scenario, we can assume that velocity in the x direction is going to be constant. Hence why we are not going to have an acceleration. If our acceleration is 0, we do not have a change in velocity. Velocity is constant. So Vx is going to be constant. So the acceleration is independent of the direction of velocity. We kind of talked about that with the vectors. The velocity vector has to follow the direction of motion, while acceleration vector, can kind of do what he wants. So for freely falling objects, for objects that are launched into the air, that are thrown into the air, we call these projectiles. So we assume with projectiles, whether they're being dropped or launched or thrown, like the picture shown here, we are going to assume that acceleration is pointing down. Gravity is pulling the object back down. So we're going to assume that the acceleration vector is down, but the velocity component is going to follow the path of the motion. Gravity does not change. Acceleration and gravity does not change. It is the same acceleration pulling you down. Okay, so the basic equations of projectile motion. They are very similar, if not exactly the same, as your basic kinematic formulas. The only things that are different is that you will definitively see x and y differentiated. So you have your horizontal equations. Those are the ones with the x's, v sub x, or just x itself for the position. This only deals with the horizontal motion, the horizontal component. And we assume that for horizontal, our acceleration horizontally is 0 because our velocity is constant. So our final velocity is the same as our initial velocity. These three equations down here are the vertical equations for projectile motion. They are similar to your kinematic formulas. The only thing that's a little bit different is instead of putting A for acceleration, like AY, they use G. You can see this both ways. I've seen textbooks where you just have A, or textbooks that just have G, but they are both the acceleration of gravity because it only affects the vertical component. So if you see just normal y, that's position in the y direction, the vertical direction. Okay, when you have objects that have a 0 launch angle, where the launch angle is going to be the direction of your initial velocity with respect to the horizontal axis. So when you measure angles, you are doing it with respect to the horizontal axis, to the x-axis. So in this case, your initial velocity in the y direction is 0. So when you think of projectiles like this, think of a parabola, an upside down parabola, because that's kind of what they look like. So your initial vertical velocity is 0. It goes up and up and up and up. When it gets to the top, that vertical velocity is 0 at the top. So Vy at the top is 0. When it comes back down, it is going to increase in velocity only in the negative direction. So that same chart we saw in the last lecture, that would be a really good one to reference and go back to for this. Okay, if you have a projectile that is launched horizontally, so think of pushing a ball off a table, and it goes so far off the table and goes down. That's what a projectile launched horizontally looks like. So you can see that it has some height starting out, right? If you're rolling something off a table, it has some height already. It goes down and down and down and down until it hits the ground or the origin point. Your vertical motion is accelerated by gravity, but your horizontal motion is uniform, meaning it covers the same amount of distance in equal time increments. So in this case, your object is moving 1 meter for an equal amount of time. It could be 1 second. Your vertical component, you can see the distances are getting bigger with every second that passes, or whatever time interval this is in. This is that acceleration of gravity happening, that change in velocity. Okay, so if you eliminate time and you want to find height as a function of x, okay, I know I said that finding x and y components together is not super common, but in this case, for zero launch angle, it is. So you can find the landing point or the x distance by setting your height to 0, and then you would solve for x that way. So that's the equation here, down here. And this is derived from the y equals a plus bx formula from algebra, which is your parabola equation, which all of the graphs for projectiles are parabolas. All right, your components. So if you launch something in the air at an angle, you have vertical and horizontal components for velocity and for position. So your x component, just like we did before, uses your cosine function. And then your vertical uses the sine function. So if things are launched at angles, your equations that we talked about earlier change a little bit. Instead of just having regular Vx and regular Vy, now you have to include the component. So your V cosine of theta, your V sine of theta just replaces your Vx and your Vy. It's all you have to do for the angles. All right, so in this example, you have different snapshots of a trajectory, which is a fancy way of saying its path. So the red pinkish dots are at time 0.5 seconds, time 1 second, and 1.5 seconds. So you can see the parabola shape. You can see it's getting higher into the air. It's increasing in the y direction. It's getting further away from the origin in the x direction. All right, some key characteristics of projectile motion. Some common vocab words you'll hear. You will hear range. That just means the horizontal distance your projectile travels, the x value. If your initial and final elevation or height, your y value, are the same, then to find your range, so your r, you can do your initial velocity squared over gravity times sine of 2 theta. This is derived for you. This can help you find your range as long as you are in the perfect world and you start and end at the same elevation. And it doesn't have to be 0. You could start your elevation at 2 meters and end at 2 meters, and this would still work just the same. But you use your velocity squared divided by gravity times sine of 2 theta. And remember, your theta is your angle with respect to the x-axis. Okay. Other key characteristics, especially when it comes to angles. So, your horizontal range is going to be the maximum value it can be if your projectile is launched at 45 degrees. That's kind of like the magic angle. If you want something to go the furthest horizontally, you need to launch it at 45 degrees. You can figure out the range max using velocity squared divided by gravity. On this graph, you can see different ranges and the different angles. Now, these lines These are lines in the real world. So notice how the parabolas aren't equal on both sides. This is not ideal world. This is real life. So in the perfect world, 45 degrees would put you the furthest away. It would come out even further if my line was, symmetrical. But I want you to compare the real world, right, these, and then compare the ideal situation. Here we go. Here is your ideal world situation. Parabola symmetrical on both sides. At each elevation, each height, you have the same velocity on both sides. One's just negative, one's positive based on the direction.